Yeah, I know.
I'm glad that we can talk today. Then we don't have to make up the lab.
Yeah.
What are you gonna do with the 2 feet?
Next week I already built in a buffer of no labs, so we'll just make that.
Oh, nice. Yay. Oh, for next week.
Yeah, but I'll go over all that.
Check your 13 live notes out.
Oh.
I wanted to ask you about a map thing that I wanted to review with you.
Bro, I had still got school today. Like, I don't get out until 11.
It's like, there's always kind of sitting there, and I think in high school I had messing with people, like I go, and then I go so bad. It's fun though.
It just like we suck.
I know, I was.
Okay.
Most of my teachers got in the air, and then our writing teacher was like, get it together.
None of my teachers. Well, our health teacher did.
No. Oh, no, no. That's always the most. Okay.
Yeah, it's okay. But just like, I was I bet you heard.
I met like 4 people through my, I met
That's all right. That's all right. Yeah, I'm just so behind.
Oh, yeah. There's a comic class.
Really Shakespeare and those.
Come on.
Yeah, you're missing.
It's like, okay. Katie, I can't really draw like I want anything, but that's new. So like,
Yeah, I need
to go through all this. It's just like a. Yeah.
All right, let's get started here. All right, so let's go over what we're going to do, and because we have a lot of stuff to talk about since the disruption. All right, so if you made it to class today, thank you. And so for lab people, let's just start. So next week is your midterm. So don't forget about that. I had a mistake on the syllabus. Somebody pointed out I had the wrong date for the midterm, so I apologize. It is next week. We do need to have your midterm next week. It's already pretty late in the quarter to have a midterm on week 6, so yes, we need to proceed. So next week, right, we'll do our review on Tuesday. Thursday, we'll take the midterm. And so then let's talk about labs. So if you're here, and so we can kind of obviously talk about this more in detail, but right, my thought was the regular Thursday people would still have lab today, like usual. So we're doing the titration lab. And then if you can't make it, or you're the Tuesday lab, so if you look at the syllabus, we were already planning to not have lab next week. I usually build that in so that you get a week off, but it works when we have, time off like this, unfortunately. So we'll make it up next week. And then if you need to make up something on Thursday or you were just missing labs anyways, we can still do makeups. So makeups Thursday as well. And if we need to do Friday, we could also do that. I know some people had talked to me about maybe doing a Friday makeup tomorrow, but then I didn't get back to them because I don't know what the weather is going to be like, so I don't know if they're going to be canceling RCC tomorrow or if y'all would be able to make it, especially since so few people made it today. But yeah, so that's that. So we're going to try to quickly go over chapter 16 today, but I do want to pimp out more volunteer stuff. So I met with the Boys and Girls Club, and they were very excited. So they want people to volunteer. And so again, we're supposed to maybe have a meeting tomorrow, but I just have a feeling that's not going to happen with the weather. So just email me. A few of you have already emailed and spoken to me, so I haven't forgotten. So keep emailing me. And I think I'll probably just send out maybe an electronic sign up to start off with. And so what you can kind of be thinking about is they're looking for volunteers to kind of commit to either a Wednesday day, so if that works for your schedule, and then maybe some other volunteers that could either do a Tuesday or Thursday. So that's kind of more immediate. And then for the future to think about, and again, I'll try to send out a survey, but I want y'all to think about this. But for the future in the summer, so if you're going to be around in the summer, they do this like Boys and Girls Club summer camp thing, and so they really want, some volunteers that would be around for the summer and maybe want to help with that camp. And ideally, they want to come to RCC and have a tour around here too. So just something to think about. So if that, excites you and you think you'll be around in the summer, definitely let me know. Email me. And then, like I said, I'll probably send out a sign up. Things got a little weird this week, obviously, with the snow. And who knows what tomorrow will hold. All right, any questions about makeups and all that? And then if you're missing the quiz, just try to get it in by email. I know people were emailing me for the quiz, so I'll email those back. And otherwise, just try to make those up ASAP like next week. All right, so let's kind of quickly go through the chapter. Luckily, this was like it's an easier chapter, I think, so if you had to learn it on your own, I think it's okay. Hopefully you watched the video and, kind of the introduction. Obviously, this is kind of an appropriate topic, too, since we're looking at the snow outside. And if you notice, RCC salted the roads, and so part of that, is kind of this antifreeze property. And let's kind of just skip this. So basic concept, and again, ask questions, So I told you come with questions to class. So if you didn't understand stuff from the video, we can kind of quickly cover it today. So main point, solutions. We have our solute, which is usually a solid, but not always, Could be a solid. It's also called the minor component. And then our solvent is the major component, usually. And then for our purposes, we're usually working with aqueous solutions of water as our solvent, but then obviously you'll move on to organic chemistry and have all sorts of organic solvents. And then blah, 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 just something to keep in mind is, again, like dissolves like. And so that has to do with their polarity, And so the example that I gave y'all, at least your warning, was people like to clean up hexane or oil spills with hexane, and both of these are straight chain hydrocarbons, nonpolar. So like dissolves like, again, you're thinking about the intermolecular forces. And then, right, obviously something that's polar mixes well. So obviously, right, ethanol water was one that we've seen. They both have hydrogen bonding. So again, like dissolves like. So that's kind of the basic. And then, right, the main thing about this chapter is it's trying to introduce you to all these different units of concentration. And so this is probably, right, your cheat sheet for this chapter is just all summarized right here, what you need to know, and then the rest of this chapter is just kind of practicing that. So we'll do a few examples and we'll point out some things. And so your most common one that you're going to use is molarity, of course. I think we've used this, right? Moles over liters. So just star that, whatever. And then we also have molality, which is not used so much, at least in the chemistry world, but in other cases where you might want a more accurate volume. And so the problem with the volume is like it could vary slightly with the temperature. And so this is why molality is considered more accurate. And so notice it's moles over kilograms of solvent. But again, in practice, you usually don't see that. And then just pay attention, because right, they only differ by an R and an L. And then molarity is big M, molality is little m, so kind of confusing. And then the rest of these, y'all should be familiar with, right? Mole fraction, we just finished doing. Mole percent, right? That was on our pressure quiz. And then these are all just, again, kind of reminding us different ways that we can express our percentage, right? They can be percent by mass by volume, which it doesn't have on here. But basically, right, any combination or ratio. All right, let's do a practice, blah, blah, blah. All right, so let's try this practice problem, just see where we all are. And so we have a solution of 17.2 grams of ethylene glycol in 0.5 kilograms of water. And then, of course, right, note the density of water. It's, of course, 1 gram per milliliter. And then the final volume is 515 milliliters. So pay attention to that. And then for the solution, so calculate each of these. So molarity, molality, percent by mass, mole fraction, and mole percent. So take probably like 5 minutes to at least go through this. Flag me down if you have questions immediately. Otherwise, right, ask your neighbors, kind of walk through this.
Let me have access to the chapter 16 notes as well.
It should be going. Let me see. I think it's just syncing really slowly or something. I'm not sure. All right, let's start going over these. So then, and if you're online, type some answers in. So what do we do for molarity? What was our formula just for molarity? What was it again? So moles over liters. And so, right, we just have to pull out the appropriate pieces. So, right, we need to figure out moles of our solute. And so do we figure that out?
Yeah,
0.277 moles. Is that other people got? Yes, no. So yes. Sorry, no one said anything. All right, so yes, that's what you got. Sorry, I was pulling up my notes to verify it, and then y'all responded. And so then divided by, right, our liters. And so this is, again, where you can kind of note where things can get a little weird, right, depending with what you're using. So in this case, an ethylene glycol is this like liquid substance. So that's kind of why you have a different final volume, right? Sometimes you dissolve stuff and it really doesn't make a difference in the volume. But that's what we use. And so then what do we get for the molarity for A?
0.54.
So 0.54. Excellent. All right, questions on molarity. So again, right, that's just moles over liters. All right, so now let's try, so what's molality? What's that formula? So moles over kilogram. And so now we can move a little faster, right? So it's still 0.277 moles, since it's still the ethylene glycol. But then again, right, this is where you could argue that this molality is slightly more accurate since we're dividing it by our mass of water. So 0.5 kilograms of solvent. So then what do we get for our molality? So you said 0.55? Yep. So everybody got that? So 0.55, and then that's little m. Admittedly, it's hard to tell with my handwriting. All right, molality with the L. All right, what about percent by mass? So how do we do that one? So total amount of mass. So we have 17 grams plus 500 kilograms. So about 517.2 grams. And then, so then we could find our percentage of each. And again, right now we're doing mass per mass. We could have done mass per volume. It's just whatever you're asked for. And so then, right, we have to calculate it for both. So the ethylene glycol, we then take the 17.2 grams over 517. So So what percentage did we get?
I got
0.033, so then that'd be 3.3%. And then we can repeat that right for the water. And of course, you could also just take 100 minus that since there's only two components, or do 500 over 517.2. Pull up my calculator. And again, just showing, right, addition would have gotten us there anyways. So 96.7% roughly for the other one. And again, right, just watch the units. I think that's the theme of the class. What's mole fraction then? So how do we get mole fraction? Yeah, so we need, right, moles of what we're interested in. So it's just like the partial pressure, right? So it's whatever moles we want over our total moles. So I'll hand back your quiz today from last week. So same concept as your quiz, again, right, with the partial pressures. And so let's put together what we have, right? We already solved for moles of ethylene glycol, so now we just need to solve for moles of water. So moles, ethylene glycol, still the same. So 0.277, and then so moles of water, somebody's telling me it's 18 grams per mole for our molecular weight. So how many moles of water do we get? None? So 27.75 or 27.8 roughly. So that sounds good. And remember, you have to add them. And so now, right, for the ethylene glycol, to find the mole fraction, so 0.277 over the total moles, so 0.277 plus 27.8. So then I get barely anything, so like 1% for our ethylene glycol mole fraction, so 0.0098, or like barely 1% for the ethylene glycol, again by mole fraction. And notice, right, mole fraction and mole percent are basically the same thing, right? It's just the fraction, the percent you multiply by 100, and then, right, usually you work with the mole fraction in the math. Questions about these basic concepts?
Can we get the table printed out? I still can't access the notes online.
Okay, yeah, I'll print that out for during the quiz. I don't know what's up with the notes. I think It's supposed to be up to date. That's what it tells me. All right, the last little bit we should talk about, or at least I'll just point it out because it's in the notes here. But when we're doing like parts per million, so remember a part per million is 1 part over, right, 1 times 10 to the 6 parts. And to me, this is always like confusing, or at least I get confused by it. And so I think it's easier if you convert it to these units. And so if you can see your factor here, so right, if you're in milligrams, that's 10 to the negative third. And then if you're in kilograms, right, that's 10 to the positive third. So that difference gives you that 10 to the 6 difference. So there's your 1 million factor. So my suggestion is to convert, right, your solute to milligrams and put that over, right, kilograms of solution, or set up some sort of proportion with milligrams and kilograms. And so same thing with parts per billion. Again, right, it's a part out of 1 times 10 to the 9th parts, which is again confusing. And so if you convert your solute then to micrograms and then your solution to kilograms, that will give you your parts per billion conversion. All right, let's look at other stuff. Oh, so let's talk about our Van Hoff factors here. And so the other thing that we want to think about is, of course, right, how many particles something dissolves into. And so it brings out this fancy Van Hoff factor, which is really just saying, like, how many ions is it going to make in solution? And so for us, we'll just go again for kind of the expected Van Hoff factor. You can see, right, when you actually measure it with conductivity properties, it's a little lower than expected, but again, for our purposes, we'll go with our expected here, and we'll look at the homework. And so, right, any non-electrolyte, so we're thinking sugar or molecule, right, aspirin, so that's not going to disassociate in water. So you would have your expected molarity. And so if we look at the homework, this is where this concept ties in, right? In problem 6, where it's talking about determine the ideal Van Hoff factor and then rank them in order of increasing osmotic pressure. And so before we get into the osmotic pressure trends and all that, we have to figure out the effective molarity. And so sucrose, right, it's a molecule, so it's still 0.1 molar in solution. But now if we look at like sodium chloride, so we can go back to our notes. So notice sodium chloride, obviously, right, you have a cation and an anion. It's an ionic compound, right? You expect it to dissociate in solution, just like we've been talking about. So what we're saying is 1 mole of sodium chloride becomes 2 moles of ions in solution. So then if we look at our homework, so this is times 2, so then we really have a 0.16 molar solution for sodium chloride. And then looking at magnesium chloride, so how many particles do you think this will split into? We got, how many chlorines do we have there? Yeah, so 2 Cls, 1 magnesium, so 3. So this is times 3 then for its Van Hoff factor. So then its effective molarity is 0.09. Because again, you're talking about how many particles in solution. All right, so we'll come back to this ordering, but this is the first kind of part of that, is getting its true molarity. And again, you can see that from the notes and looking at like iron 3 chloride here. Again, right, it would disassociate into 1 iron, your 3 chlorides. So 4, same thing for your polyatomics, of course, right? Keep your polyatomics together just like we're used to. And right, magnesium sulfate would split into 2 particles, so twice the effective molarity. Okay, blah, blah, blah. So vapor pressure of solutions. And so now this is starting to kind of get into, again, why we salt the roads and all this. And so the vapor pressure of a solvent above a solution is lower than the vapor pressure of a pure solvent. And so all we're saying is, right, so if we have our ethanol or whatever, right, if we then dissolve something in there, and this we should clarify should be non-volatile, because we'll talk about volatile solutions and how they add up. And so now, okay, this is also, well, this is more the argument, and now you could get into an argument about when you should add salt to your pasta, right? So it's saying, okay, the vapor pressure of your solution is lower than your vapor pressure of the pure solvent. So if you add salt to your pasta water, right, before boiling it, then theoretically speaking, now your vapor pressure is lowered, so you're going to have to add more energy to get that pot to boil. Now there's other arguments too, where like, oh, the hot water could potentially cook your pasta better, and then it's better. I don't know. Like, cooking science gets all interesting versus, you know, it's boiling at a lower temperature, and then you salt it after. And so again, right, addition, and here's a key term, of a non-volatile solute reduces our rate of vaporization and decreasing our amount of vapor. And then another phenomenon you find is if you have a concentrated solution, it will draw solvent molecules to it to mix. And so then, right, this brings us to the vapor pressure lowering here. And again, for non-volatiles, I would just keep starring this for non-volatile. And so basically, what we want to do is you want to find, right, your mole fraction. And then whatever your mole fraction is, you can multiply it by your pure solvent. So, sorry, you want this formula. So this will be more helpful. So, right, your mole fraction of your solvent times your pure solvent gives you your new pressure. And again, right, sanity check on the math. Well, your mole fraction is always going to be less than 1. And so that means, right, your vapor pressure of your solution is always less than your pure solvent. So let's try that out with the math here. So calculate our vapor pressure of our solution that contains 99.5 grams of sucrose, 300 milliliters of water. And again, right, note that it's sucrose, so non-volatile for this problem. And then, right, it tells us the vapor pressure of pure water.
What was the formula?
Above this, there was it was the salt, there was some language in there about like what the solvent above it's pretty far up, but a little further up, the vapor pressure of a solvent above a solution, not above a solution, is that just?
Oh, just like, yeah, what they're trying to say is like, right, the pressure right above it, so basically your equilibrium exchange is lower. Yeah, I think how they phrased it is kind of odd, but it's trying to say, okay, you have like 2 cups, right? And if one is a solution and one is pure, then the solution one has less dots than the pure one. But yeah, it was kind of phrased funny. So how's this one coming? So probably the hard part is getting our molecular weight of sucrose. Did we get that? 312. I have like 342 on my notes, but
That's what I have is 3.2.
so about 342.3 roughly. So somewhere around there. So if you're a little off, then your number might be off. So yeah, just double check the addition. It should be closer to there. And so then we just have to find moles of each, right? So moles of sucrose. So 99.5 grams over the molecular weight. And so how many moles did that give you roughly? So 0.29 moles of sucrose. And then we need moles of water. And right, they told us the density of water. So we can just assume 300 grams. And then over 18. So how many moles of water do we have roughly?
16.7.
So 16.7 moles of water. So perfect. And so right now we can get our mole fraction. And so remember we want it for water, right? So we can get our solvent. And so now, so I'll just say, right, calculate for H2O, our mole fraction. 16.7 over 16.7 plus 0.291. And again, right, you're just kind of sanity checking yourself. It's like it shouldn't be too different. The primary component is still water. Oh, it would help if I could enter number. So then, right, this is our mole fraction. And then we just want to multiply this by the original vapor pressure. So the pure water vapor pressure is 23.8 torr. So now we can take this, multiply it by 23.8. And right, it's just a little lower, which is what we expect. So our new vapor pressure is about 23.4 torr. Okay, questions?
You solve for the water first because it tells you more rather than doing one minus the pressure it takes away when you're having to solve it.
Yeah, I mean, either way, right,
There.
yeah, because, right, you could have done this weird, like, pressure lowering, but I don't like that one. So it's just straightforward, yeah, to find the mole fraction of your solvent.
Skip the steps, we're just moving past the steps.
Yeah, because this is kind of more straightforward. All right, so let's look at other properties. And so again, now we're getting into why they salted the roads. So we have freezing point depression. And so now we're saying that the freezing point of a solution is lower than the freezing point of a pure solvent. So yay, right now we've explained why they salted the roads. So they made a solution, right, thus lowering the freezing point. And again, right, use your units to kind of guide this. So whatever your change in temperature is, so this is, right, your difference in temperature between your solution and your pure solvent, and this is going to be related to your proportionality constant and its molarity. And so again, right, you can kind of see where the information will guide the math. So you'd have to be given the proper KF, and then notice the units of KF, at least in this book, are tended to be given in degrees Celsius per molality. So just watch that. We don't often use molality. And again, right, that's just moles over kilogram of solvent. Just remind yourself. And then this graph is nice. It's just kind of showing you, right, so this is again our triple point graph like we saw earlier. And now we're appreciating the pure solvent and how it decreases for our solution, right, for that liquid solid line. So there's our freezing point depression. And so blah, blah, blah. Again, right, you have to be given KFs. And then, so we kind of touched on it in the previous page, we just didn't say it. So now we can say boiling point elevation, right? So if your vapor pressure is lowered for a solution, that means that your boiling point has to be higher, right, to now achieve that. And again, this is for a non-volatile solute. And again, same thing, just like the freezing point, you have a difference in boiling point between your solution and your solvent. Your pure, it's going to be dictated again by your boiling constant, again dictated by those units or whatever units you would be given. All right, so let's try to do this problem. So what, actually I'm going to copy it twice. Sorry. So I'll put the question up here because you're going to need some information from the chart. So what is the freezing point of a 1.7 molal, and then watch the wording, aqueous ethylene glycol solution. So I'll give you a minute or two to kind of figure that one out. All right, so just to keep things moving, so I'll just do it here actually so we can see the chart. So again, right, on an exam I have to give you probably just the normal freezing point for safety, and then right, either your KF if we're talking about freezing point, or again, right, KB if we're talking about boiling. And so first we can just find our change in temperature. So again, right, use the units to guide you. So the KF is degrees Celsius per molality. And so for water, and this is the only tricky thing about this problem, is it says aqueous ethylene glycol. So you have to recognize that your primary component is water. So that was kind of tricky with this particular wording. But then we're looking at this KF, so 1.86. We're given our molality, so at least we don't have to think too hard about that. So now this gives us how many degrees it's going to differ by. So 1.86 times 1.7. So then we get this 3.126, but then remember it's freezing point depression. So then you can find your new freezing point. So now negative 3.162 degrees Celsius. So chat looks like it's on it. Does that make sense for everybody? All right, so we'll keep it moving again to kind of speed through this chapter. Let's see, osmosis. I don't have too much to say about that. Just it's defined as a flow of solvent from a solution of low concentration into high concentration, and they have to be separated by some sort of semi-permeable membrane. And then we have our osmotic pressure, which we can also find if we ever needed to calculate it. So again, note your units. So R is our same gas constant. And we should just add in, right, the Van Hoff factor. That's the only thing that's missing from this equation is, right, you need to take into account how many particles it will make. And then you do want to know these terms. So these are important for this chapter. So isoosmotic or I'm more familiar with the term isotonic, but either one to be familiar with those terms. So isotonic, right, is when your red blood cells have the same solution concentration, right, as the fluid, the rest of it. So we have same equilibrium across. If you have a hyperosmotic solution or hypertonic solution, right, then you have more particles outside of your cell. So this would kind of be, maybe you had too much salt in your diet, an extreme case, and then your poor cells are shriveling, right, trying to get water out of the cell to, again, bring equilibrium, right? So it's always about trying to make the concentration the same, or isotonic. So, right, isotonic is equilibrium. Since, again, right, no net flow of water, so it would be the same both ways. And then hypotonic, this is like why the gallon challenge stuff can be deadly. So, right, you chug a gallon of water or whatever, and now your solution has a very low concentration of electrolytes, let's just say, and so then the water would flow into the cell, right, to try to, again, equilibrate for that. And obviously, right, worst case scenario, your cells could burst. So, all right, last little bit. So I do want to talk about the last bit here about Raoult's law. And so now this is for a volatile solute. And so blah, 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 right? If the solvent and the solute can both evaporate, then obviously, right, both molecules are found in the vapor phase. And so before, again, we get into it, so just an ideal solution, our total pressure would just be, right, if we added kind of the two of them, right, in a partial pressure manner. And what we want to say, though, is, well, we want to look at these deviations, right? And so basically, here's what we're saying. So we have, let's just say we have an ideal solution. So again, assuming just no interactions really. So this is kind of ignoring, right, our intermolecular forces is what this is getting at. So if we just have our two components and add them, right, linearly, here's what we expect. So, right, we're saying we have 100% component of B starting over here, and then it's equal to the vapor pressure of B. And then the rest of this is just completely additive. And so now what we care about is the deviations. And so let's understand what causes those deviations. And so if you have stronger solute-solvent interactions, right, than it does with itself, then that can, of course, cause a lowering of your expected vapor pressure. So again, it's just all about those intermolecular forces. But then if you have weak solute-solvent interactions, then, right, you can have a higher vapor pressure than expected. Again, just additively. And so let's go through how we would calculate that. And so we have our solution here. So it contains 3.95 grams of carbon disulfide. And so carbon disulfide, right, is a gas. It's volatile. Well, it's a volatile liquid, excuse me. So it is a liquid, but it's very volatile. You don't want to breathe it in. And then 2.43 grams of acetone. So it tells us the vapor pressure of pure carbon disulfide and pure acetone are 515 and 332 torr. And so it says blah, 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 right? Calculate your expected vapor pressure, kind of assuming ideal behavior, and then compare that to the experimental pressure of 645. So kind of think about how you would approach this, right? Thinking about from our solutions before, right? From the non-volatile. I'll give you a minute or so to get started and then we'll go over it. So we'll start going over it, but there was a good question in the chat just kind of asking how we know if it's like a normal or a volatile problem. And so, right, so you kind of have to think about what you can be asked. So, right, normally, if you're looking for something normal, then you're looking for a non-volatile, right, substance, something that's a solid. But let's say, you know, you're given this scenario. We still have to treat it normally first is kind of the situation, right? So we're still going to treat it normal. We're still going to figure out, right, the expected vapor pressure. But then again, it's the deviation that tells us. So let's go through that. So what do we have to solve for these problems? Yeah, moles, since we need to get moles and moles fraction. So let's do that. So CS2, we have 3.95 grams. What's the molecular weight? 143 grams. And so then how many moles does that give us? 0.052. Bless you, moles of CS2. Okay, so let's repeat that for acetone. So just getting moles of each still, so 2.43. And then what's the molecular weight of acetone?
58.0.
58.08, thanks. And then how many moles does that give us? 0.042 moles of acetone. So this is looking good. And again, so now we have to solve for the mole fraction of each and get, right, its expected vapor pressure. And so 0.052 over our total moles. So what does that give us? I can plug it in as well. And I'm watching the chat too for answers. So 55%, excellent, I got that. So 55.3 roughly for our CS2. And then we can repeat our mole fraction for acetone. Or subtract, so now I feel lazy. Thank you. Oh, I don't know what I did. So 44.7. I'll write out the work. Or again, right, subtracting was perfectly appropriate. All right, so now we can finally find our total vapor pressure. So, right, our total pressure is then equal to, so starting with our mole fraction of CS2, so 0.553, right, converting our percent back to fraction, times, so I have to look at, so it said the vapor pressure of carbon disulfide was 515, right, for the pure. And then plus, so then we had 0.447 times, what was our pure one? So 332 for acetone. Oops. All right, so then I get that our kind of expected, and again, right, this is how we would treat it normally for kind of a non-volatile problem. So I have 433 torr. Did we all get that at least? And so now we have to go back to what the question was asking us for. So it said the experimentally measured total vapor pressure is 645. So was our number higher or lower than 645? So lower, right? So now we're showing, okay, well this is actually higher than what we expect, right? So now we can kind of go back to our chart here. Right, so we were expecting something a little lower, additively speaking. It was much more higher. And so now this is telling us something about those solute-solvent interactions. And you can start to kind of maybe puzzle out why this would be the case, right? So it's telling you we have weak solute-solvent interactions. And then just kind of thinking about it, right? So carbon disulfide, what do you know about carbon disulfide? What's it analogous to? Okay, that's annoying. If you just Google CS2, you get Counter-Strike. What's it analogous to? So it's covalent, but is it polar, non-polar? Yeah, non-polar, right? Because it's just like CO2. So there's carbon disulfide. So right, pretty nonpolar. We could also look at, where's its, I was looking for the dipole moment.
Oh, I saw it, 0.
Oh, yeah, so 0 for the dipole moment, right? So again, just emphasizing super nonpolar versus acetone. So, right, if you remember what acetone looks like, it gave you the formula C double bond O here. So it looks like that. So, right, we have a carbonyl group, so at least somewhat polar. We could compare, if we want to put a number on it, compare the dipole moment for acetone. Here, there's a pretty picture of acetone again, right? Oxygen and dipole moment, right? 2.88, so much more polar. And so just that, right? So again, you have something that's relatively nonpolar versus something that's polar. So there's unlike, right? Well, we said like dissolves like. So this is why they do not have strong interactions, and so then that makes sense for that deviation there. So then you can talk about the relative strength, right, of those interactions. So they're pretty poor interactions. The carbon disulfide and acetone is what we're getting at. All right, still more to this chapter. Last little bit is, again, right, formulas that are dictated by their constants. And so basically, how much gas can you dissolve and pressurize is dependent upon this Henry's law constant. And, right, basically, this lets you know what pressure you have to pack it in for whatever desired solubility. And then again, last little bit. So gases are kind of the opposite of solids in a lot of ways. I like saying that. Gases, opposite solids. And so what we mean by that is, right, usually for like the majority of substances, if you heat up a solid, right, that helps it dissolve. But then gases have pretty poor solubility already, since they tend to be nonpolar. And so that means that the solubility decreases as the temperature increases. So the opposite, right? So you heat it up, and that makes the gases just fly out of solution. And so that's what's illustrated here with the cold versus the warm soda. So, right, if you pour out the warm soda, it's extra fizzy, right, because all the gas is escaping, and it's not dissolved in there. And so again, blah, 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 right, you can supersaturate your gas solution, low temperatures, high pressures, and then, right, you've all seen when you shake your carbonated beverage and it becomes unstable and fizzes everywhere. Similarly to how, like, you know, you can put the Mentos in the diet soda, and then that has to do with like some sort of nucleation on there where it causes, again, the gases to become unstable. All right, so we could try this one for good measure, but let's recopy it, because again, it's all dependent on these constants. Oh, sorry. So again, right, you have to be given your Henry's laws constant. So what pressure of carbon dioxide is required to get your concentration in your club soda at 0.12 molarity at 25 degrees Celsius, so just telling us we can use this constant. All right, so just to finish up this one, so again, right, we're given this desired concentration, so 0.12 molarity is equal to, we have to be given our KH in a problem. So this time we're looking at CO2, so 3.4 times 10 to the negative 2. And then let your units guide you, so molarity per ATM. So that means we just need to solve for ATM there. So 0.12 then, divided by that 3.4 times 10 to the negative 2. And then that gives us a pressure of 3.5 ATM. So again, a lot of little formulas, but I don't think they're too bad, since again, those units really help kind of guide you.
What, maybe, I'm just confused as to why, like, the molarity was brought into the solid fluid.
Oh, because that's like how much you want
That was,
in
like, the
there.
end of it.
Yeah, because it's asking like how much is going to be in there, right? Like what's the concentration? So it's saying, well, you want a desired concentration of 0.12 of CO2, so that's where you plugged it in there. And then, right, your KHP is just telling you how much pressure you have to apply for that certain gas to achieve that. But yeah, again, right, I have to give you the KH for any problem, so I think that'll kind of help give a hint for those. All right, other questions? I know we kind of went through the chapter quickly, but if you watched my last year's lecture video, that should help. I'm just trying to think if there's any other big concepts, but I think that's basically most of them. Any other last questions, comments for this chapter? So I will print out, right, y'all wanted the cheat sheet. So this, yeah, so I'll print that out. Hopefully the note's updated. I don't know what they're doing. Tells me they're up to date. But I'll print that out because, again, right, this is kind of your short and sweet of this chapter. Use your notes for it. And then we'll review more on Tuesday, right, of anything that will come up on the exam, hopefully. All right, I'll stop talking for now, and then I'll hand out our quiz so we can at least do the quiz, and then, of course, take a break if you need to. And then if you're online and need a quiz, just email me. Oh, are you ready to take the quiz?
Yeah.
Okay. Okay. I'm going to keep the stream running for another second or two in case there are questions.